Hello students, let's begin our lecture number 5, and during this initial time of the lecture I want to say to you some message about practical class tomorrow. There is some problem, and a teacher of 167 group is ill today. Is ill today. I hope it will be fine across maybe 2 weeks. But tomorrow we will deliver again practical class for both of 66th and 67th group together. And in this aim, it's not a good idea to use TrueConf program. TrueConf. In this case, remember, tomorrow look in the folder practical class practical class number 4 and use link. It will be again translation in the YouTube channel like today's lecture. And tomorrow we will consider methods of the pH calculation of the pH for different solutions, and tomorrow we will consider theory on hydrolysis of the salts. Well, and after tomorrow, in the interval between practical class number 4 and practical class number 5, you will deliver test about calculations and so on. Well, it is information about next time, and now let's continue our theory. Please send me in this message. Is it good translation, or there are any problems with the voice, with the vision, anybody else? So anybody send me a message. Is it good or not? Well, and we considered acid-base equilibrium, and we told that electrolyte, it may be acid or base, may be more stronger, maybe less stronger, and the quantitative characteristic of the electrolyte strength is ionization constant. Just a minute, ionization constant. For example, this ionization constant for acetic acid, ionization constant for weak base, aqueous solution of ammonia, and appropriate method is using of negative of the logarithm of ionization constant, which is labeled as pK. pK is equal to the negative of the logarithm of the constant. And comparison of the different acids and bases. Look at this table. Comparison shows that if ionization constant is larger, this given equilibrium between acid and conjugated base If constant is larger, this equilibrium is shifted to the left or to the right, depending on the value of the constant. And now let's consider amphiprotic electrolytes. Amphiprotic electrolytes, it means that this compound is dissociated in the aqueous solution, and this solution has both of acidic and basic properties. Depending on the characteristic of the solution, depending on the pH, and depending on the other reactant. And it's better to consider amino acids. Amino acids, it's organic substance which consists of two different functional groups. COOH, it means carboxylic group. It is typical acidic group. COOH group is a typical donor of hydrogen ion. And amino group NH2, which is a typical weak basic group, weak acceptor of proton. But if we look on the definition of the amino acid, it's known that these amino acids are crystalline substances which have a large solubility in the water. Why? The large solubility of the water means that in nature it is any charged species. And look at this slide. In the center, if we combine proton donor group together with proton acceptor group, COOH group together with amino group, dissolving in the water means proton transfer. H plus is transferred from carboxylic group on the amino group. And in this case, any amino acid in the aqueous solution, any amino acid has a form of double ion, which is denoted as Zweiter ion. It is in the center of this slide. What is double ion? It means that carboxylic group is ionized, and in double ion it has negative charge, COO negative, and this proton is accepted by amino group, by the nitrogen of amino group. And look at the center. It results in protonated amino group. It results in H3N or NH3 cation, NH3 positively charged group. And this double ion is uncharged, totally is uncharged, because plus 1 and minus 1 together results in zero charge. But it means that this double ion can't be attracted by the cathode, neither anode in the electrochemical cell, and electric conductivity of aqueous solution, ordinary initial aqueous solution of amino acid is equal to the electric conductivity of pure water, because the form of amino acid in the initial solution is a form of double ion, or Zweiter ion. Zweiter, it means German name of this species. I want to repeat, the total charge of the double ion is 0, and it can be denoted as isoelectric state of amino acid, isoelectric state of this amphiprotic electrolyte. Isoelectric state, it means that total charge on the species is 0. But let's add any acid to original amino acid solution. Addition of any acid means shift to the left on this slide. Compare left structure with central structure. Difference is 1 proton. COO negative group is an acceptor of proton. It is potential acceptor of proton, and it is exposed to added acid. It results in COOH neutral form. In this case, charge, it will be +1. It is a charge of protonated amino group, and that's all. So, in acidic solution, we can say that in acidic solution there is cation of amino acid. Cation of amino acid, and it is a charged species. And look on the graph. It is electric conductivity across the pH. Addition of the acid means decreasing of the pH of solution, and electric conductivity rises dramatically. Why? Because equilibrium between cation and double ion is shifted to the direction of cation. Concentration of the charged species increases, and electric conductivity is correspondingly increased. But if I'll add any alkali, any weak or strong base in the original solution of amino acid, it means that added hydroxide anion is a strong acceptor of the proton. It means that double ion of the amino acid is exposed to alkali, and it results in deprotonated form. It means anion. Look in the first line and look on the right side of the slide. Now, nitrogen loses its third proton, but COO negative remains the same, and the total charge of this species is -1. So remember that in the alkalinic solution, amino acid is negatively charged. Amino acid is negatively charged in the alkalinic solution. And again, look on the graph. Electric conductivity increases dramatically if pH rises. Why? Because isoelectric state of amino acid is transferred into negatively charged form. Concentration of anions of amino acid rises, and electric conductivity is correspondingly raised to. But quantitatively, let's look on this theoretical scheme using quantitative characteristic of the ionization. From the center to the left, quantitative characteristic is ionization constant of carboxylic group, or negative of the logarithm of the Ka. For the glycine, for the typical amino acid, which can be found in the typical protein, for glycine, this pKa1, it means negative logarithm of the COOH ionization constant, is about 3. Negative logarithm is about 3. Constant itself is about 10 upon minus 3. Well, look from center to the right. In this case, quantitative characteristic is ionization constant of the amino group, and negative the logarithm of the second ionization constant, it means pKa2 of amino group, is about 12. Is about 9. It means that the second ionization constant, Ka of amino group, is about 10 upon minus 9. And look on the graph again. It is important characteristic. What is the pH of the amino acid solution when electric conductivity has a minimum value? Electric conductivity is a minimum value, and what is the pH of this solution? This pH is denoted as isoelectric point of the solution, isoelectric point, and it is labeled as Pi. So I told there are two different terms. Isoelectric state is a form of double ion when total charge +1 and -1, total charge is 0. It is denoted as isoelectric state. Isoelectric point is the pH of given solution. And underline, isoelectric point is the pH of amino acid solution. Isoelectric point, Pi, is the pH of amino acid solution which has minimum of electric conductivity. Which has minimum of electric conductivity, because of amino acid has a form of double ion, a form of isoelectric state. When and how is it possible to calculate isoelectric point Pi for the ordinary amino acids? Isoelectric point is a medium value of pKa1 and pKa2. Look on the second line. It is a half of the sum. pKa1, pKa of carboxylic group, is about 3. pKa2, it means pKa of amino group, is about 9. And the medium value is about 6. Exactly speaking, for glycine, isoelectric point is 5.99. 5.99. Or roughly speaking, it's about 6. Well, and it is a very, very important information about amino acids and their polymers. It is a very important information about proteins and peptides. For ordinary protein, isoelectric point is about 6. There are different exceptions, but ordinary situation, isoelectric point for our proteins is about 6. But the pH of our organism, for example, the pH of blood is about 7.4. The pH of the blood is larger than isoelectric point of ordinary proteins. It means that the proteins of the blood, the proteins of the muscle tissue, are the proteins has any negative charge. They are negatively charged in the state of our living organism. And it is a very important, because in this case proteins of the blood are soluble in this liquid. Solubility increases correspondingly to the charge, and physiological function of the proteins of the muscle tissue is corresponding to their any delocalized negative charge 2. And this isoelectric point is a very important information for analysis of our blood or any other tissues in the clinical laboratories. For example, today we are exposed by COVID-19, and their favorite analysis is analysis on the special peptides, and these peptides give the information about the presence of the viruses in the organism of given patient. And one of the methods of the analysis is electrophoresis. It means a motion of peptides along electric field. And this motion is exactly corresponded to the isoelectric point. So, if we know the isoelectric point of the special peptide for COVID-19, we can deliver this analysis very correctly. Okay. And now let's continue and consider next section, which is acid-base buffers. So, underline, next section is acid-base buffers. In previous section, we told that the physiological function of the protein or peptide, anybody else, is corresponding to the pH of solution. In this case, it's a very important, it's a favorite function of the blood or another tissues to deliver a constant or approximately constant pH, constant acid-base equilibrium. And it is possible using acid-base buffers. Underline, what is an acid-base buffer? Acid-base buffer is a solution characterized by the ability to resist changes in the pH, changes in the pH when limited amounts of strong acid or alkali are added to it. When limited amounts of strong acid or alkali are added to it. Tomorrow on the practical class, we will calculate the change of the pH of the pure water. Pure water when we will add any amount of strong acid, for example, hydrochloric acid. But today I want to say you this conclusion. What is pH change? pH of pure water, you know that pH of pure water is about 7. If I'll add 1 milliliter of concentrated hydrochloric acid to the pure water, which volume is 1 liter, so 1 milliliter of concentrated hydrochloric acid to 1 liter of water, pH change will be about 5 units. 5 units, it means from 7 to 2 approximately. And this pH change is dramatically large, very large. But if I'll use a buffer, for example blood, and if I'll add 1 milliliter of concentrated hydrochloric acid to the 1 liter of the blood, pH change will be about 0.1, maybe less. So it's a very, very small value, and it is a buffer action. Our blood plasma is a typical acid-base buffer. So, what is the function of acid-base buffer? If I'll add strong acid to given aqueous solution, buffer solution, the pH remains the same. Roughly speaking, pH remains the same. Why? Because our buffer consists of buffer base, buffer proton acceptor, and buffer base will neutralize added acid. In this case, pH is approximately the same. So remember, buffer must consist of buffer base. But if I'll add any alkali, sodium hydroxide for example, to the same buffer solution, the pH remains the same again. Why? Because our buffer solution consists of buffer acid, buffer proton donor, and buffer acid will neutralize added alkali. In this case, pH can be the same. So, on one side, buffer consists of both of buffer acid and buffer base. It's needed for buffer action. But on the other hand, why buffer acid is not neutralized by buffer base? Why is reaction of neutralization absent in the case of the common presence of buffer acid and buffer base. And the explanation is the only one. Buffer acid and buffer base, underline, is buffer acid and buffer base form a conjugate acid-base pair. Conjugate acid-base pair. In the previous lecture we told that if any acid is ionizated, any acid results in proton plus anion. Acid is a proton donor, but on anion is a conjugate proton acceptor. It means conjugated base. And the term of conjugated acid-base pair means that in any cases, in aqueous solution, there are both of species, conjugate acid plus conjugate base every time for any situation. But now let's look on this situation on other hand, on other words. What is the difference between buffer acid and buffer base? How can we find in the test, in the control work, the pair of species which will be a conjugate acid-base pair? Remember, underline, difference between conjugated acid and conjugated base is the only proton. Difference is one hydrogen ion, a single hydrogen ion. And in this case, we can say that if we want to prepare acid-base buffer, we must take acid-base conjugated pair. Conjugated acid-base pair. It is necessary condition for preparation of the buffer. But on other hand, we can say that strong acid is conjugated to appropriate conjugate base. Is it possible to use strong acids or alkalis for preparation of buffers? No, because buffer action is corresponded to the relatively large amount of the both of buffer acid and buffer base. Buffer action is corresponded to the relatively large number of moles of the both of buffer acid and buffer base. For example, in the liter, we must have 1 mole of buffer acid plus 1 mole of buffer base, or any other amounts, but it must be relative large amounts, large number of moles. In this case, using of strong electrolytes is impossible. Using of strong electrolytes, for example, strong acids or strong bases, alkalis, is impossible. Conjugated acid-base pair, underline, must be reversible one. And in this case, acid-base conjugated pair is one of weak acid or weak base. If we want to prepare buffer, we must construct conjugated acid-base pair using weak acid and weak base, and that's all. And what are the types of the buffers in this case? It may be acidic buffer. Underline, acidic buffer consists of weak acid and its salt. Any weak acid and its salt. Basic buffer consists of weak base and its salt. Amphiprotic buffer is a solution of amino acid itself, one amino acid at given pH. And before the break, let's consider the first type of buffer. It means acidic buffer. The typical example is acetate buffer. Acetate buffer. Acetate buffer consists of, just a minute, acetate buffer consists of acetic acid, weak acetic acid, and on salt. For example, sodium acetate. Sodium acetate. If we want to explain the buffer action of this mixture, let's look on the dissociation of both of these components. It is more easily to consider dissociation of the sodium acetate. This is ionic substance and it is a strong electrolyte. Look on the second line. Dissociation is complete and irreversible. Sodium acetate gives acetate anion and sodium cation in aqueous solution. But a weak acetic acid wants to give the same acetate anion and a proton. In this case, we have a complex mixture and common ion effect takes place. Common ion effect is a shift of equilibrium at expose of the same ion of both of electrolytes. Look, acetate anion is resulted from dissociation of the salt, but acetate anion is resulted from dissociation of the acid. But equilibrium, there is equilibrium for the only weak acid. In this case, dissociation of the acetic acid is depressed. Dissociation of the acetic acid is depressed approximately to zero. Approximately. And roughly speaking, we can say that amount of the moles, number of the moles of acetate anion is equal to the number of moles of the salt, but number of the moles of the neutral acid molecules CH3COOH is equal to the initial number of moles of the acetic acid. During preparation, we know what is number of these moles, what is a volume of solution, concentration of solution, which were used for preparation. And remember, in the case of the buffers, you must convert volumes, concentrations, masses into number of moles. A favorite units for the calculations are moles. Moles, only moles. So, for example, I took 1 liter of 1 mole per liter of sodium acetate solution. 1 liter of the 1 m solution. It means that I took 1 moles of the sodium acetate. It means that in the aqueous solution there will be the same 1 mole of acetate anions. And I mix this solution with 1 liter of, for example, 0.5 mole per liter acetic acid solution. 1 liter of 0.5 m molarity of acetic acid was 0.5 mole per liter. In this case, what is number of moles of the neutral molecules of acetic acid? In complete solution, in given buffer, acetic acid is not ionizated, and it means that number of the moles of the neutral molecules CH3COH is equal to the 0.5 moles. It is initial amount of the acid which was used for preparation. Continue. What is conjugated acid-base pair in this buffer? Look, compare CH3COOH molecule and CH3COO negative anion. These are components of the reversible conjugated acid-base pair. Difference is 1 proton. Molecule is a molecule of weak acid, and CH3COO- is a needed conjugated base. Let's now break for maybe 3 or 5 minutes. No more than 3 or 5. 3 minutes. 3 minutes break, and after that we will continue. 3 minutes break. Okay, dear students, let's continue. Let's continue, and next step is discussion of buffer action. Buffer action. Remember, if you will find in the test, in the counterwork, questions about change of the pH, questions about buffer action or buffer effectivity, and everything else. The first step is writing all these chemical equations, which shows equations which show the reaction between added strong acid or added alkali and components of the buffer. So the first equation can be denoted as buffer action against added hydrochloric acid. Buffer action against added hydrochloric acid. Hydrochloric acid is a proton donor according to the Bronsted concept. In this case, hydrochloric acid must be neutralized by buffer base. Buffer base or conjugated base is acetate anion, CH3COO negative ion. But what is the source of this acetate anion? A single source is the presence of the sodium acetate salt. So this is a quantitative chemical reaction. It means that 1 mole of hydrochloric acid can be neutralized by 1 mole of sodium acetate, and it results in 1 mole of acetic acid and sodium chloride. And what are variants of the questions on the test or control work? So maybe the first variant of the question: what's happened? We can say that the amount of the salt, sodium acetate, decreases, but the amount of the acetate acid, the second component of the buffer, increases, which is resulted from this buffer action against HCl. The second variant of the question: what is quantitatively? What are quantitative changes? What are changes quantitatively? We can say that number of moles of the sodium acetate decreases, but this change is equal to the number of the moles of HCl. Amount of the acetic acid increases, but number of the moles, change of the number of the moles is equal to the number of the moles of HCl again. Well, the third variant of the question: how many moles of HCl can be added to given buffer before the end of buffer action? How many moles of HCl can be added to given buffer? Look, HCl reacts with sodium acetate. So we can say that, roughly speaking, amount of HCl must be less than number of the moles of the sodium acetate. Before the break, I told, as example of the buffer, the amount of the moles of sodium acetate is 1 mole. It means that amount of HCl must be less than 1 mole. Less than 1 mole exactly. And the next variant of the question. For example, you will have different buffers, different components, different compositions, and everything else. Which buffer is more effective against HCl? Which buffer is more effective? Look, HCl reacts with buffer base. HCl reacts with sodium acetate in given example. So, in each buffer, you must find buffer base. After that, calculate number of the moles of the base of the buffer, namely buffer base. And if this number is greater than that for other buffers, this buffer will be more effective against HCl. And tomorrow, I hope tomorrow, we will begin studying the buffers, and I'll repeat these questions, and we will solve some tasks about this. Look on the second line. It is a buffer action against alkali. Buffer action against alkali. For example, added sodium hydroxide is neutralized by acetic acid, which is resulted in preparation of sodium acetate and water. And it is a quantitative reaction again. So, 1 mole of sodium hydroxide is neutralized by 1 mole of acetic acid, and it results in 1 mole of sodium acetate and 1 mole of water. And again, let's consider the same variants of the questions. What's happened? In this case, amount of the acetic acid decreases, but amount of sodium acetate increases. Well, what are these changes quantitatively? What are these changes quantitatively? So, decreasing of the moles of the acetic acid is equal to the number of the sodium hydroxide, number of moles of sodium hydroxide. Increasing of the sodium acetate, increasing of the number of the moles of the sodium acetate is equal to the same. Increasing of the salt is equal to the number of the moles of the neutralized alkali. Well, how many alkali can be added to given solution? How many moles of alkali can be added to given solution, to given buffer before essential change of the pH. Amount of the moles of the alkali must be less than the number of the moles of the buffer acid. Before the break, I told in my example, number of the moles of acetic acid is 0.5 moles. In this case, a possible amount of sodium hydroxide must be less than 0.5 moles, exactly less. It can't be equal. The less, only less than that for acetic acid. Well, and before different buffers, which buffer is more effective against alkali? Which buffer is more effective against alkali? In this case, the first step, in each buffer, you will find a buffer acid. Calculate the number of the moles of the buffer acid in each variant, and if the number of the moles of buffer acid is larger than that for other variants, this variant will be more effective against alkali. Well, in the section of the acid-base buffers, there are two favorite questions. What is the pH of the buffer? And what is a quantitative characteristic of the buffer action? pH can be calculated using Henderson-Hasselbalch equation. In this slide, Henderson-Hasselbalch equation is presented. How is it possible to understand this formula? Let's consider the dissociation of acetic acid. After that, let's write expression of the dissociation constant for acetic acid, Ka. After that, we can rewrite this formula for H concentration, and after that, let's take the negative of the logarithm, and negative of the logarithm of the proton concentration results in the pH value. Negative of the logarithm of the ionization constant results in pKa value, and other concentrations of the CH3COH molecules and concentration of the CH3COO anion will be presented as ratio under the logarithm. So, in this case, the pH of any solution, and namely for buffer is one of the application of Henderson-Hasselbalch equation. So the pH is the sum of two parts. The first part is the value of ionization constant exponent, pKa. This value can be found in literature, in textbook, in database. For example, for acetic acid, pKa is 4.76. 4.76. This is negative of the logarithm of ionization constant for acetic acid. And the second contribution is logarithm of the ratio. Equilibrium concentration of proton acceptor, it means buffer base, which is divided by the equilibrium concentration of the proton donor. It means buffer acid. Buffer acid. And before the break we told that sodium acetate is completely dissociated, acetic acid is not dissociated at all. In this case, the second contribution can be rewritten as logarithm of the ratio. In the numerator, remember, salt, it means number of the moles of the salt, which is divided by the number of the moles of the buffer acid. Remember, I told number of the moles of the sodium acetate was 1 mole in my previous example. Number of the moles of the buffer acid, acetic acid, is 0.5. So, under the logarithm, ratio is 1 by half. It means logarithm of 2. Logarithm of 2. And after that, pKa of acetic acid is 4.76 plus logarithm of 2. And let's take calculator and calculate logarithm of 2. It will be 0.3. 0.3, it means that final pH is approximately 5. Approximately 5. And let's analyze this answer. Final pH in my example, in my buffer example, is about 5. It is larger than the value of pKa of acetic acid. pKa is 4.76. This is standard experimental value. Amount of buffer base is larger than amount of buffer acid in 2 times. What is result of this? Any base, in my example, it is sodium acetate, rises the pH. Any acid and buffer acid just the same decreases the pH. Excess of the sodium acetate means rising of the pH, and 5 is larger than pKa. Final pH, which is 5, is larger than pKa of acetic acid. It means it is larger than 4.76. And it means that it is correct. It is correct. Now, let's consider basic buffer. What is a basic buffer? Basic buffer must consist of a reversible acid-base conjugated pair. But in this case, we must mix weak base plus cation of this base. Cation of this base will be resulted from the dissociation of appropriate salt. And a typical example of the basic buffer is ammonium buffer. Ammonium buffer is an aqueous solution of NH3 in the water and plus appropriate own salt. For example, ammonium chloride, ammonium sulfate, ammonium nitrate, NH4NO3, and so on. And in this case, look on the Henderson-Hasselbalch equation. Just the same. pH is the sum of the two contributions, where the first contribution is the negative of the logarithm of the base ionization constant, and the second contribution is the logarithm of the ratio base by salt. Base by salt. pKb for aqueous ammonia is 9.25. pKb for NH3 in the water is 9.25. And we can prepare different buffers, excess of base, excess of salt, or the same amounts. In this case, we will have different values of the pH. So, put it on other hand. What are different variants of the buffer? Looking on the Henderson-Hasselbalch equation, we can say that the first difference will be difference between components, one-to-one, or excess of acid, excess of base, excess of salt, anybody else. In this case, ratio under the logarithm differs, and in this case we will have different values of the pH. And the second variety is dilution. For example, in the case of acetic buffer, under the logarithm, ratio was 1/2, or logarithm of 2. But if I'll add water, any amount of water, and if I'll dilute my original buffer in 2 times, in 3 times, in 10 times, anybody else, amount of the moles of the salt remains the same. Volume rises, but number of the moles of solute, salt or acid remains the same. In this case, ratio remains the same and pH remains the same too. But is any difference of diluted buffer or concentrated buffer? Yes. Difference is one of effectivity of buffer action, and quantitative characteristic of the buffer action is buffer capacity. Quantitative characteristic of the buffer action is buffer capacity. And there are 2 values. BA is buffer capacity for the acid, look for HCl, and for the alkali there is other buffer capacity which is labeled as BB, buffer capacity on the base. What is buffer capacity? This is amount of the moles of strong acid or alkali which was added to our buffer, number of the moles of HCl or sodium hydroxide which was added to our buffer, to 1 liter of our buffer. It was added to 1 liter of the buffer, which gives pH change on 1 unit. Delta pH is 1. And using these formulas, you can calculate the value of buffer capacity. If you will find a question which buffer is more effective, you can calculate this buffer capacity on acid or base and compare. If value of your buffer is larger, it means that buffer action or buffer effectivity is larger too. Let's look on this graph. Effect of the added acid or base on the pH of a buffer. So, this is a graph for sodium acetate buffer. It means mixture of acetic acid and sodium acetate salt. In the center, amount of the added acid or base is 0. And pH, according to Henderson-Hasselbalch equation, is equal to the pKa. It means it is equal to the 4.76. But addition of acid will result in decreasing of the pH. Addition of the base, addition of the alkali will result in increasing of the pH. But when number of the moles of the proton or hydroxide anion is 0 to 0.5, pH change is relatively small. The red area on this graph is the area when our buffer is effective one. But if amount of added acid or alkali is larger, graph shows that pH change is dramatically increased. In this case, buffer effectivity is not appropriate one. In this case, we can ask, what are appropriate compositions of given buffer? What are appropriate compositions between salt and acid if we want to have effective buffer? Look, this equation is corresponding to Henderson-Hasselbalch equation, and on the other hand, this equation will be rewritten as what is pH of appropriate buffers? What is pH range of appropriate buffers? Looking on Henderson-Hasselbalch equation, we can say that a logarithm may be +1 till -1. Put it on other hand. If logarithm of this ratio is equal to 1, it means that amount of the salt is larger than amount of the acid in 10 times. Logarithm of 10 is 1. And pH is larger than pKa on 1 unit. But if logarithm of the ratio is equal to -1, it means that ratio is 1 by 10. It means that amount of the acid is larger than amount of the salt in 10 times. Logarithm of 1 by 10 is -1, and pH in this case is pKa -1. And for acetate buffer, we can say that pH range of appropriate buffers is pKa, it means 4.76 plus minus 1. And it is an experimental evidence according to this experiment graph. Well, and now let's begin consider buffers of living organisms. I told that blood, tissues, any organisms have a definite buffer properties. And in our organism, we can select 4 different buffers: protein, hydrocarbonate, hydrophosphate buffers, and hemoglobin. What's about protein buffer? The function of the protein buffer, the action of the protein buffer, peptide buffer, likes to the action of individual amino acid into aqueous solution. Look on previous slide. pH of our organism is larger than 7. Exactly speaking, the pH of the blood is equal to 7.4. Isoelectric point of an ordinary protein is about 6. So, according to this slide, we can say that at the conditions of our organism, any protein is presented as composition of 2 forms: isoelectric state, when charge is 0, plus anion, plus negatively charged structure. Difference between isoelectric state, this is a central scheme, and negatively charged, this is a right scheme. Difference is 1 proton. In this case, any protein, peptide, or individual amino acid acts as buffer in the case of our organism. Now, what's about hydrocarbonate or hydrogen carbonate buffer? Carbon dioxide, CO2, is ordinary substance in any tissue of our organism. Carbon dioxide is dissolved into water and form H2CO3 molecule, carbonic acid. This is ordinary weak acid, and carbonic acid is decomposed on the proton. It is dissociated onto proton and hydrogen carbonate anion, H plus and HCO3 minus. On the down of the slide, you can see the Henderson-Hasselbalch equation for this mixture. 6.1, this is the negative of the logarithm of the first ionization constant for normal conditions. It means for 37 centigrades. Ionization constant 1, the pKa 1 of carbonic acid is 6.1 plus logarithm of the ratio. Look on numerator. This is a concentration of the buffer base. It means concentration of the hydrocarbonate anion. But look on the denominator under the logarithm. This is expression of the amount of dissolved carbon dioxide into water. S is solubility constant, P of CO2 is a partial pressure of carbon dioxide over the blood. And look on the right, 0.033, this is a solubility constant. It means constant for the solubility of carbon dioxide into blood at physiological conditions. And again, P is a partial pressure of namely CO2 over the blood. Or put it on other hand, this is amount of carbon dioxide in our air after lungs. Well, we know that pH of our organism is 7 and something. It means that the value of the logarithm is about 1. It means that concentration in denominator is less than concentration in numerator in 20 times approximately. Put it on other hand, we can say that in the case of the living organism, concentration of buffer base is larger than that for buffer acid. Why? Because our organism is exposed by carbon dioxide, and our organism must resist to action of carbon dioxide. In this case, it's needed to have excess of buffer base to avoid the action of acidic oxide, CO2. Next buffer is hydrogen phosphate buffer. Hydrogen phosphate buffer is constructed using 2 anions of phosphoric acid. It means H2PO4 negative and HPO4 2 negative. And again, we have mixture of species which are differentiated by 1 proton. And again, it is a composition of weak acid and appropriate salt, and after that we can write Henderson-Hasselbalch equation, and ionization constant exponent is 6.8, And after that, logarithm of the ratio 2 negative anion by mononegative anion. And again, if our pH is about 7 and something, the value of the logarithm is about 0.5 and everything else. And again, we have excess of buffer base comparatively to buffer acid. To buffer acid. And in this point, let's consider why did we use the second stage of dissociation of phosphoric acid? Because pKa1 is about 3, pKa2 of phosphoric acid is about 7, 6.8 exactly, and pKa3 for the third stage of phosphoric acid ionization is about 12, and everything else 11 or 12. So in this case, for physiological state, for physiological conditions, when pH will be about 7, it's impossible to have equilibrium using the third stage of phosphoric acid ionization, and just the same for third stage of ionization. Appropriate pKa is pKa2 for phosphoric acid. In this case, we can prepare buffer which can form the pH about 7. And in previous hydrogen cabinet buffer, again, pKa1 is about 6 and something for H2CO3, pKa2 is about 11. But put it on other hand, there is not any liquid, any fluid in our organism where pH will be about 11. We must have pH which is about 7. In this case, it's needed to use the only first ionization stage of this acid. And the last information about hemoglobin buffer. Hemoglobin buffer. Later in the coordination compounds, we will consider hemoglobin molecule again. But now we can say that hemoglobin protein is needed for transfer of oxygen from lungs to tissue. And there are two different forms of hemoglobin molecule. It may be hemoglobin itself or hemoglobin together with 4 oxygen molecules. Look on the second line. Addition of the oxygen molecules forms oxyhemoglobin. When hemoglobin is saturated by oxygen, it is denoted as oxyhemoglobin, and it is labeled as HBO2. Hemoglobin itself is labeled as HB in the first line. But the presence of the oxygen in the oxyhemoglobin will result in change of acid-base equilibrium. Look, pKa of hemoglobin itself is 8 and something. pKa of the oxyhemoglobin is less than 7. This difference is larger than 1 unit between hemoglobin and oxyhemoglobin. What does it mean? It means that if pKa decreases, acidic properties increase. So, underline, oxyhemoglobin is a more stronger acid. Oxyhemoglobin is a more stronger acid than hemoglobin itself. So, at first, it shows the important pH for oxygen transport. If pH will be changed, pH of the blood will be changed, oxygen transport will be broken, will be destroyed. And at the second, if I'll add any acid to hemoglobin system, it means a mixture of both of hemoglobin and oxyhemoglobin. So, if I add for any acid, any proton to the blood, this proton will be accepted by a more stronger base. A more stronger base, look at the first line. This is anion. It is negatively charged structure of the hemoglobin itself. Remember, buffer action of the hemoglobin system against acid is reaction of the added proton with anion of the hemoglobin itself. But buffer action of hemoglobin system against alkali, look on down. Buffer action of hemoglobin system against alkali is reaction of hydroxide added with a more stronger acid. A more stronger acid in this case is molecule of oxyhemoglobin, HBO2. So, alkali is neutralized by molecule of oxyhemoglobin. Well, time is over. Thank you very much for your attention. See you tomorrow, and we will calculate the pH for different solutions, and we will try to begin study buffer systems together. That's all for now. Thank you very much. Goodbye.